I know everybody's tired, myself included. It's not going to be a long talk because I feel a little bit like a redundant over complete basis vector. Since everybody else has talked about this and everybody else has more experience than I do in the subject. But we'll do a little bit of an overview and what we have been working on. So just for the people who are not familiar, I am part of the Dini group working with Hervé. I am the postdoctorate student there. And I'm working under the Cognilego project. If you look in the beginning of the books, the first 2 pages, I think, refer to that project. It was actually one of the reasons why this summer school is happening. So the goal of the Cognilego project, which is from pixels to semantics, in broad terms is to try and come up with biologically plausible models for the automatic hand-written text and digit recognition. So that's something that's been happening for a long, long time, and for me it's something new, and I'm very willing and eager to take on the challenge. Now, one of the things that we've been looking into under this project is the use of sparse constraints in deep architectures. And we think that that might help in some tasks like domain adaptation. I'm going to start this talk by giving a little bit, a very brief overview, since Jan did it in such a brilliant way, and honestly one of the best ways that I've seen so far. I'm going to give a very brief overview of the energy-based models, and then restricted Boltzmann machines, which fall under the category of energy-based models. And then I'm going to get into that notion of adding sparse constraints to the restricted Boltzmann machine that is a building block for a deep belief network. And we're going to look at this general sparse penalty that was proposed by Hastings and Tibshirani and see if it's something we could actually apply on the restricted Boltzmann machine. And it's comprised of a mixed norm, which is also something that Jan talked about, and an L1 norm. And then I'm going to proceed by trying to show if it has any effect on domain adaptation tasks. And by domain adaptation task, we mean basically that we train on one set of digits, but we test on a different set of digits, and we want to see if our models are able to generalize across those different training and test sets. So that's basically what I would refer to as a domain adaptation task. So energy-based models in general, you can consider them as neural networks that are comprised of a set of visible and hidden units. And what the model does, what the energy model will do, is it will assign a probability, a joint probability, which is going to be defined based on this energy function, normalized by the partition function. And the partition function, which is there to ensure that we're talking about a probability, is something that becomes an obstacle because, as Jan and Marcel and other people mentioned, it's not so easy to analytically compute. There's a lot of literature out there, but unfortunately it's not that easily tractable. Usually what we do in the case of energy-based models, again, to learn the parameters of the model, we perform gradient descent on the negative log likelihood. And what we want to basically achieve is a lowest energy state. Now, when we take the gradient of the negative log likelihood and we apply some math, it turns out, and I'm trying to go a little bit fast on this, since we've been through it a little, we've been through it before with Jan. So when we go through the math, what we actually get is this gradient that is comprised of 2 phases, a negative phase positive phase. So in the negative phase, what we're trying to do is increase the energy of all x in the model. Again, we're increasing the energy, thus, as Jan mentioned, we're decreasing the probability of all the possible data that we can have. And for the positive phase, what we're doing is we're decreasing the energy of the observed x in the model, of our training data, basically, and thus increasing their probability of occurring. So what happens is, again, we have that difficulty of computing that first part, that negative phase part. So that's in general for the energy-based models. The restricted Boltzmann machines are a special category of an energy-based model, and what we like about them is that they're restricted, which basically means that we have the conditional independence between the hidden and the visible units, which makes things a little bit easier. The energy is a function of weights and biases that is provided here. And the other thing, in most cases, and in the simplest case, both your visible and hidden units are stochastic binary units. Now, that's great for modeling images such as digits, where you can sort of say we have a binary thing, but doesn't work for natural scenes. In those cases, there are other things you can do, like using Gaussian visible units, which are basically your visible units with some added Gaussian noise. And that would work for natural scenes, for example. But in this case, and for us, because we're focusing on digit recognition, we can use the stochastic binary units. So, going back to that main gradient derivative that we saw in a couple of slides before, the parameters of the model, which are the weights, the biases for the hidden and the visible units, can be provided by these update equations. Again, as I mentioned before, we have this problem of actually computing the derivative for all the model, for all the data in the model. This is one of the issues and one of the obstacles when it came to using Boltzmann machines. But what Hinton proposed was to use the contrasted divergence, whereby you can just try and sample from that distribution, as Jan mentioned before, by using a Gibbs sampler. And again, one of the good things about the restricted Boltzmann machine is because you have those independencies and your units are not connected, you can do those updates simultaneously. So one of the things that's interesting is that from what it appears and from what I've seen in the literature, this type of using the contrasted divergence does not actually follow the gradient, but it works practically, and I think that's important for the whole concept. So what I've done here, just to give, I know it's like baby steps, but for people who may not be familiar with some inner workings, or the way I was not familiar. So here is an example of some sample learned weights for a 500 hidden unit RBM and 100 unit RBM. So to the left you have the 500 unit. Fortunately, I think I don't know if it looks very well or if you can see the differences, but the whole idea, this is just a sample, it's not all 500 hidden units, because otherwise it would be difficult to see, but the whole idea is to show that the number of hidden units is really important in your architecture. The more hidden units you have, the more expressive you're going to be able to be in trying to model your underlying distribution. The lower the number, on the other hand, you're not going to have that expressiveness, and it sort of shows up in when you look at these weights and what it is that they're trying to model. So this is an example again for the same type of architecture. So on the left, for when you have a 500 hidden unit RBM and a 100 hidden unit RBM, this is an example of the visible units when you sample from the visible units, and you actually see what it is that your RDM is generating. So this on the left is on the case for the 500 hidden units, and on the right 400 units, where you can see that there is that noise, and possibly they're not enough to actually express the underlying distribution. Now, sparsity has become extremely important, and I think for multiple reasons, aside from the fact that you have that ability to, when you have like an over-complete basis, when you blow something up and then you're able to have only a few variables turned on, then if you want to classify, you might be able to discriminate better and use just a linear classifier, so you basically have that. And you also, I think, have the ability to concisely capture information. I think that's another important aspect of having that sparse constraint. One of the easiest way to induce sparsity in a restricted Boltzmann machine is to add what's called a weight decay, which is just a regularizer on the square sum of the weights. And that's something that Hinton has also done, and he has provided a lot of tricks and tips on how to use these regularizers and what are the best ways. So he has actually provided a range for this type of regularizer. Now, this will not exactly, when I say sparsity, it's not going to turn weights into zero. So this will try and push them, soft them, push them towards zero. That's the whole idea behind it. So to give you an example of how that looks for the different values of lambda, because now your parameter lambda, the regularizer, actually makes a difference on what it is you're modeling and how you're modeling it. So if lambda is really, really low, then you're basically capturing more and more information. So it's not as important, in quotes, the penalty. If lambda is really, really high, on the other hand, then that penalty becomes really important. And the only way you can minimize the cost function with the added penalties by pushing those zeros towards zero. So this is the whole idea. Here you can see that when lambda is really, really low, you have a more expressiveness in the weights and filters that you've learned. Of course, you always run into the danger of possibly overfitting. When lambda is really, really high, you have the opposite effect. Things are getting more smoothed out, and again, you might run eventually the issue of actually underfitting your underlying distribution. So in a similar manner, if you sample your visible units to see what it is you're actually learning, what you're generating, then you can see the differences, you can see that noise that is as part of that reconstruction, depending on the different values of the regularizer parameter. So those are the basic that was the first easiest way of inducing a sparse constraint in the restricted Boltzmann machine. And the idea was, again, because we want to have this sort of domain adaptation task, whereby if we train on one type of digits, data set of digits, let's say the NIST database, but we test on a completely different data set, which is, I don't know, for example, the rhymes data set. We'd like to be able to have some sort of generalized and robust results. They may not be great, they might not get really high accuracy, but we'd like to get some robust results. And the idea is, well, we're dealing with digits, so some things, some structures should be similar across the different data sets. So is there a way to somehow capture that by adding sparse constraints? One of the interesting penalties that came by were proposed by Tibshirani and Hastings, and it's called a sparse group lasso. Now, it wasn't proposed in the framework of restricted Boltzmann machines and DBNs. It was proposed in the framework of optimization and sparse coding and in that type of a framework. So we wanted to see, is there any way that we can somehow tweak that or employ that on the RBM framework? So the idea would be to impose this kind of penalty on the activations of the hidden units. So basically we would somehow, in quotes, guide how these units fire. And it's what Jan was also saying before, is to put that structure on these activations, okay, on these filters. So this is not something, you know, what Hastings and Tibshirani did, they proposed this large general penalty, but this is not something that hasn't been done in deep AI. It has been done, although in different contexts or one by one, not all together. So the mixed norm has been done by Luo, by Li and Ang. Again, they might not be all on the RBM, it might be on the autoencoder or other variations of deep networks, but they have been there with similarities. The same for other L1 norms with the Ranzato paper. So this is not something that's completely new, it's just a general sort of penalty that brings everything together. The way you would learn this penalty is similar to how you did before when we did gradient descent, but now you have to do it blockwise. So in order to be able to update the parameters in a correct way. So you still use contractive divergence and you use a block coordinate descent for the sparse mixed norm. And again, what happens now is you have these two new hyperparameters, the L1 and the L2 hyperparameters, that would basically define how these penalties play in the model. So you do enter this symphony of hyperparameters that you now have to tune and deal with, which is also one of the issues that at least I have found working with these deep architectures. So by having this new cost function, having added the mixed norm, the sparse mixed norm, you can actually, doing some math and taking the gradients to extract the new update equations for the parameters of your network. And once you have that, you can then start and play and see if anything happens at all, if there is some difference. What we have done here is using the sparse mixed norm RBN on the MNIST data set, choosing the different hyperparameters, and that's one big issue, how you choose those hyperparameters. And most of the times what I've seen done from other researchers is using brute force, building a grid and then trying from there, based on the type of data that you have, to find the best sort of combination of these hyperparameters. So we, for this case and for these experiments, what we did is a little bit of a greedy search, and also trying to see from literature that was already out there, because there's so many experiments that have been done on digit recognition. So a lot of these things are already, in a way, fixed. So we know more or less what the good ranges are for these hyperparameters. So by using these existing ranges of hyperparameters, we tried to see if there was going to be any difference in our system. So you can see an example, just a sample of some of the learned rates when you're using the sparse mixed norm RBM. And on the right, what you see is an average of the activation probabilities when on the x-axis is for a regular restricted Boltzmann machine that has no sparsity, and for the y-axis is for the sparse mixed norm RBM, where you'd see sort of that it's like a separation. It's like things are being sort of dragged towards 1 and 0. And you get some, and these are averages. So again, you're not going to be able to see individuals. You're not going to be able to see that big sparsity happening since you're adding for the different for the sizes of the batches that you have. So this is for the sparse mixed norm. And again, when you play with the different hyperparameters and regularizers, what you can do is you can say, okay, I only want to have a mixed norm sparse penalty, or I only want to have a sparse penalty, or I don't want to have any of it. So it's you have that ability to tune that through the hyperparameters. So if you set L2 equal to 0, you can then only have a mixed norm, which again implies that you're dividing your hidden units in groups. And in this case, the groups are non-overlapping, because dealing with overlapping groups is something that we're now starting to sort of understand in the case of the restricted Boltzmann machine. I know in sparse coding it's already done, and
it's hard. It's much easier if they don't overlap.
Oh yeah, yeah. So I don't, I came across, and we can, because it's my last slide for that one. I came across a paper on sparse coding for overlapping groups and graph from he's from France.
So Renaud Genaton?
Something with I have his paper. Well, but his idea was to concatenate W actually. So that could be something that can be more easily employed on the restricted Boltzmann machine. But anyway, so the same example again, if you're dealing with only a mixed norm, again you have a sample of the weights that are learned. For me personally, I was not able to find huge differences between the different weights. It's hard to understand just from that. Again, I can see that separation of the average activation probabilities, some of them going towards 0 and the other was going towards 1. And in the same manner, for if you only use a sparse penalty, then you see again the sample of the weights, and you see all those activations being dragged towards 0, again because these are averages. You're not going to see those individual differences of the sparsity, but you don't have that sort of pull. Now in terms of a deep belief network, once you have a restricted Boltzmann machine and you have induced your sparse constraints, what you can do now is actually build a deep belief network, and you do that by stacking restricted Boltzmann machines one on top of the other. And although this was supposed to change the world, we had the issue of how we're going to train this humongous thing back in the day, and then Hinton came along. And he saved the day by saying, well, what you can do is you can do a greedy pre-training of each layer, and that will help a lot. And then you can jointly train this whole network at the end, and it will be tractable, so you will be able to train it. And fine-tune those weights. So this is what really changed everything in terms of how the use of these networks exploded in machine learning, and also gave rise to all sorts of other different kind of networks, which was really interesting for me to see that, when you talk about a deep belief network, it's very different from a deep RBM, from a stacked autoencoder, from a stacked RBM, or whatever other architecture. So there's a lot of architectures there. They all do, of course, they're all based on the minimization of some cost function with the addition of some sparse constraint, but these are all different architectures. They might have a different type of training, so it's interesting to see those variations as they come along and what it is that connects them or not. So once you have the DBN, what we did is we tried the different architectures on 3 different data sets, the NIST, the RHYMES data set, and the UPS, to see if we were going to get anything that was going to be better from what we've already have on digit recognition, which is with just a simple deep belief network. And it's hard to beat that. I mean, it's already at 98.83, and I think it might be even at 99 with some small other variations, just by using your regular deep belief network with no sparse constraints whatsoever. So there is not much in terms of gain for this specific task. However, you might see a gain when you use those sparse constraints for natural images or for some other type of task. But in this specific task, the slight maybe gain that you might see is I wouldn't consider it statistically significant to be able to say, okay, there's a huge difference if you use this kind of norm or this or the other kind of norm. Now, when we actually went into the, this is just to show what, how these sparse constraints are pushing towards 0. These are the average probability density functions for the activation probabilities, for the expectations of the activation probabilities. The top is the log, and the bottom is just the average. And you're just seeing that the sparsity is actually pushing these activations towards 0. It's just a little way to show that. But it's also doing the opposite by making that separation and sending some to 1 as well. So for the domain adaptation task, again, what we wanted to do is to generalize the performance of a model when the data classes remain the same. So you still have to actually recognize digits from 0 to 9, but the observed data, your domain changes. So again, you know, we train on one and test another, and so on and so forth. So we use 3 different data sets, the RHYMES, the USPS, and the NIST data sets to cross-test train. All images were resized because the RHYMES and USPS data sets have different sizes, and the RHYMES data set, for example, has non-uniform sizes, so each image is a different size. So they were all resized to meet the NIST data set size. Here are a few examples. What's interesting to see is, and at least what I found interesting is how at least for the USPS, there is not a lot of room around the digits, so it's, you know, the bounding box is pretty tight. And then what we did is we decided to run all these different architectures and see if they provide us with some insight on what happens when you apply these models for domain adaptation, and see if we can get actually some generalization, something robust when you're actually training and testing on different data sets, but you have the same classes, you have the same problem and same task that you're trying to solve. Now, for the case of the vanilla deep belief network, and these DBNs, just to note before I get into this, where the typical DBN that's used for digit recognition, and that is comprised of 3 layers. The first layer has 500 units, the second layer has 500 units, the third layer has 2,000 units, which is that expansion that we were talking about, and then you have your discriminative layer on top of that, which is just 10 class softmax layers. And that is your most typical deep belief network that has been in use for digit recognition in the field. So we use the same setting and the same architecture and tried to see if we were going to be able to get those some sort of generalization amongst the different data sets. For the case of the vanilla DBNs, again, whatever is in bold, it means that that architecture for that specific pair had the highest accuracy. So for example, for when we trained on NIST and tested on UPS, we got a 53.8% accuracy when using the vanilla deep belief network, and that was the highest accuracy for that specific train test pair across the different architectures. The same happened for rhymes in NIST. And then we used the mixed norm DBN, just the mixed norm DBN, and we got the highest for UPS and rhymes. And for the sparse, we were able to get the NIST rhymes and rhymes UPS, but, and finally for the sparse mixed norm. The reason why I'm going a little bit fast on this is because there's really not much of the conclusion that we can draw. We're not seeing a significant change or a significant increase. We're also not seeing some sort of robustness across the different accuracies between the different pairs. So they do happen to have a lot of variation. So you can see like a 30% difference amongst the different sets, but you're still dealing with the same task, which is to classify digits. Now, looking at the data set, if you can actually try and come up with some sort of reasoning behind this, you know, maybe it has to do with the resizing, maybe it has to do with little transformations from data set to data set, the type of how the digit is actually centered around the bounding box. I mean, these could be all issues that come into play, but we would also like to see, and we would also like to continue to explore the use of even more structure sparsity that could possibly capture those prototypical, I guess, shapes within the different classes in order to be able to provide a more robust results when you're doing these type of domain adaptation tasks, where you're actually learning on one data set and testing on the other. So one of the things that we also wanted to look into, which is something that's hard to be done on restricted Boltzmann machines, is the use of overlapping groups when you're doing the mixed norm. Now again, there's Jacob and al. It was an ICML 2009 paper. So this was on sparse coding, and what they said was that a very easy way to implement overlapping group, sparse penalty with an overlapping group, is by concatenating the weight matrix, basically. And what that will do is we'll take those overlapping groups, you'll create a new model, basically, that has a larger number of units, for example, or a larger number of length of sparse code, and then take those non-overlapping groups, take those overlapping groups and turn them into non-overlapping groups. So this could be something that could be explored as a way to be used on the restricted Boltzmann machine, so that you can actually have overlapping group sparse penalty. And then that can be extended to what Jan was talking about before, which was the S matrix, and it was the 2011 NIPS paper, which would model, you can apply it on different data sets. For me, that would be ideal for these kind of domain adaptation or even transfer learning tasks, where you can actually have that S matrix, which will modulate among the two different data sets, the type of sparsity that you can have. So that's it for now. Any questions? I have a question. So, first of of all, I'd love to get Jan's opinion for the overlapping groups and how he feels that would be something that could be achieved on the restricted voltage machines and on deep relief networks. Because I think it might be a little bit more tractable if you're using it on autoencoders or sparse autoencoders, because it's quite parallel to sparse coding. But
I don't see a fundamental difference between group sparsity on RVMs and sparse autoencoders. I mean, RVMs, you can think of RVMs basically as sparse autoencoders with the symmetry constraints on the binary, binary constraint. So it doesn't seem to me like that makes a fundamental difference. But there is some sort of inherent complexity of the inference when you have overlapping pools, pool sparsity, and perhaps the splitting idea is good. I mean, I haven't heard that, but I mean, one possibility, maybe that's what they do, is you do as if the overlapping groups actually aren't overlapping.
exactly.
But then you add a term that tries to make the variables that are not different, that tries to make them the same, because they, yeah. So it's one of those, split split variable techniques. ISTA is one of those algorithms which kind of splits the code, which allows you to do optimize the L1 term first, and then you optimize with respect to the L2 terms, and then you alternate the two, and then what allows you to do this is that you split the Z variable into two terms. So that might be something of the same nature might work, but we haven't done much in that direction. I mean, it's only a matter of how fast those things go. You can do gradient descent, it will work. You just be slow. So one comment on sparse RVMs is there was some question. So I always wondered how RVMs could work at all, because in high dimensions, the pushing up kind of idea seems hopeless, because the dimension of the space is so large. The sampling has no hope of really kind of
capturing
so exploring the whole space so that the energy function takes the right shape. So there are things like persistent CD, which kind of improve the speed of convergence. But then after we started working on this sparse autoencoders, realized that the binary constraints, the fact that the hidden state in an RVM is constrained to be binary, is already kind of a restriction on the information content that just makes it work. Just for that. And then you add a sparsity term on top of it. And then that reduces the necessity for the contrastive phase. So it's kind of the point I was making, that sparsity really replaces the need for contrastive phase. I mean, the models like spike and slab RVMs, which are kind of sparse RVMs. So that's out of Yoshua Joe's lab.
Yeah, I've seen the spike and slab.
And I think Jeff has been working with some sparse RVMs, but the latest work he's been doing is actually not RVM. So, I don't know if he's moving away from RVMs, but
I think he is, because his latest, from what I've seen, his latest talks and papers are more on like those autonomous units that are
capsules.
Yeah, the capsules.
Yeah, that solves a different problem, but yeah, but it's trying to be back properly.
Okay.
Ok, on vous remercie.